Hello students, how are you all? I hope all of you are doing amazing. So welcome all of you at AriserTalent. In our last lecture, we have a discussion about few of the NTSE questions that are related to your chapter, that is magnetic effect of electric current, and today we are again continuing with the same type of the questions. So let's move to the next question. In this sequence we have, a particle is moving towards east, enters in a magnetic field that is directed towards the north and deflected in vertically downward direction. The charged particle is. So this is a very interesting question we have. So firstly we have to analyze the directions by drawing a simple diagram. A particle is moving in the east. So this is our east and the particle is moving this side. Now it is the magnetic field is directed towards the north. For this particle, the magnetic field is in north. This is our magnetic field and it is directed in north. Now, the deflection of this particle is vertically downward direction. So, we can see that the motion of the particle will be in downward direction. This is motion and the direction will be south. Now, you have to identify that charged particle. So, according to the Fleming's left hand rule, if we are going to orient the three fingers in such a way that the thumb will give you the direction of motion, forefinger will give you the direction of field, and this will give you the direction of the current. So, if I orient my fingers in this fashion, that it is our magnetic field, it is where the particle is moving, and this is the downward direction, we can say that it will be the direction of the motion. So, if I kept my fingers like this, we can say that the particle is moving this side. It means the current is going to be flowed in opposite direction. So, this path will be followed by only a single particle here, and that particle will be your electron only, because the direction of electron and the direction of current flowing in the circuit is just opposite to each other. So, we can conclude that the particle will be electron here. So, this is our motion, this is where the particle is moving, and this is our magnetic field. So, we can orient these fingers according to the Fleming's rule, and we can find out that the particle will be an electron only. Now, let's have a next question. The magnetic field lines due to an ordinary bar magnet. So, firstly, if I am drawing an ordinary bar magnet, this is our bar magnet and this is having north pole, this is having south pole, and we have to analyze the magnetic field lines. So, magnetic field lines form a closed curve. So, if I draw the magnetic field lines in bar magnet, this will be the magnetic field due to the bar magnet, and this will be the direction of magnetic field lines. Now, the first option is magnetic field lines form the closed curves. It is forming the closed curve in the center, and you can see that these lines are not following the same closed path in the ends. So, this statement is false here. Crossing one another, this statement is true we have, because these are forming the closed curves. So, this is our true statement. It is crossing one another near the poles. So, these are our poles, and you can see that they are not crossing each other or at the poles. So, this statement will be absolutely false. Are more numerous near the north pole than the south pole. You can see that the magnetic field lines magnitude is equal at north and south pole. We do not get a lines maximum near the north pole as compared to the south pole. So, we can see that again this option is false here. Next, do not exist inside the magnet, and this statement is again false. So we have only one correct statement here, that the magnetic field lines due to a bar magnet is going to form the closed loops. So these are in the form of the closed loops we have. So we can say that option number A is correct here. Option A is correct here. So you have to remember the construction of the magnetic field lines due to every element we have discussed. Maybe it may be a solenoid, long current carrying conductor, or it may be the circular loop, because these type of the questions usually arises in accordance with the statement form or the theoretical part we have. Now, let's move to the next question. The magnetic field inside a long straight solenoid carrying conductor. So you have to identify the strength of the magnetic field in a long straight solenoid. So if we are considering a long straight solenoid, so this is our solenoid having a number of turns wound on the copper wire, and we have to identify the magnetic field inside a long straight solenoid. So it is not 0, so we can see that it will not be 0. But if I am going to draw the magnetic field lines due to this solenoid, we can get that these lines will be again in this form. We will get the lines like this, such as bar magnet we have. So we can see that the strength of the magnetic field lines or the strength of the magnetic field as we go near the poles. It means if we are going towards the end of the magnet, you can see that in case of the solenoid, these lines are going to be decreased. So its maximum strength will be in the center part of the solenoid only. And if you go at the ends, or if you go at the ends or the poles of a magnet or the solenoid, the quantity or the strength of the magnetic field lines is definitely going to be decreased. So what will happen? Decrease as we move towards its end. So this option we have found here, that option number B will be correct. It is not at same at all the points, and you can see that this is not increasing at the end. So we have only one correct option here, that is it must be decreased as we move towards its ends. Now let's move to the next question in the sequence we have. Two wires each carrying current I are shown in figure. The magnetic field at P midway between the wires is described by which statement? So what you have given? You have given the two wires here and they are carrying the same current, that is I. And the point P is situated midway between these two wires. This is our point P. So which statement is correct in accordance to that P? We have to find out the correct statement here. The magnetic fields are in opposite direction and the net field is equal to 0. The magnetic field due to two wires are in same direction. The magnetic fields are in opposite direction but not is equal to 0. Magnetic field are in the same direction and equal to 2 times of the field due to the one wire. Now, the wire is carried in the current in the same direction, then according to the Lenz's law, it always opposes the course of the motion. So we can say that the magnetic field will be in opposite direction in both the cases. So magnetic field according to both of these wires and for these two wires, magnetic field will be in opposite direction. And it will be according to the Lenz's law. If the current is flowing in this direction, we have magnetic field in this direction. So you can see that if magnetic field is in opposite direction, we have the same magnitude of the current. So we can say that if it is following in the different direction of the opposite direction, it will cancel each other and the net magnetic field due to these two wires will be equal to 0, because these both are opposite cases. So we can say that the magnetic field will be in opposite direction and it will be definitely equal to 0. So we can say that option number A is correct here. So this is again a very different question we have seen. So such type of the questions you also have to keep in your mind for your competitive exam only. Now let's move to the next question in this series we have. An electron moving with uniform velocity in x direction. You can see that electron is moving in the x direction, enters in a region of uniform magnetic field in the direction y. So this y will be the direction of magnetic field. And this will be denoted by B. Which one of the following quantities is non-zero and remains constant? So you have to identify among the options that which quantity is non-zero. So electron is moving in the x direction and the magnetic field is given in the y direction. So let's check the options first. You have to identify which quantity remains constant and non-zero. Speed of the electron. As the velocity is given, the speed cannot be 0, it may be non-zero and it must have a constant value. Momentum of the electron. Momentum is basically given by the product of mass and velocity. So if the velocity is not 0, how the momentum can be 0? So it will again be non-zero. Kinetic energy of the electron. Kinetic energy is basically given by half mv square. So if the velocity is not 0, again the kinetic energy will remain constant and it will be our non-zero quantity. Force on the electron. Force will be given by QVB sin theta. Again there is a velocity factor. So we can see that all of the four quantities will not be 0 and they will having some constant value, because the speed will be denoted by V. It will be given by P equal to mv. It is given by half mv square and force will be given by QVB sin theta. So in all these factors we can find out that there is a velocity factor. So we can see that all the four statements will have some constant value. So let's check the options here. Only 1 and 2, only 3 and 4, all 4, only 2 and 4. So we have the correct option that all 4. These all 4 quantities will going to remain non-zero. So this is again a very different question we have. Now let's move to the next question in this sequence. Again we have a diagrammatic question which is completely based upon the direction. So you can see that how the important is Fleming's, Maxwell's and other rules for analyzing the direction in each case. Uniform magnetic field exists in the plane of the paper pointing from bottom to top. So the magnetic field will be from while a proton and electron are moving from left to right. So you can see that proton and electron are moving from left to right. So the direction of So what you have to identify here, let's check the question. You have to identify the force experienced by them. So you have given a direction of electron, direction of proton and the magnetic field lines, and you have to analyze the force experienced by them. So it can be found out according to the again Fleming's rule. So if I am considering the Fleming's left hand rule, we can see that magnetic field is from top to bottom. So this line, forefinger, will give you the direction of field. So this is the magnetic field we have. So if I am assuming or visualizing my left hand, this is our magnetic field. Electron is moving here. So the direction of current will be from here. This is the direction of magnetic field. This will be the direction of current, and thumb will going to give you the direction of the force. So let's check the options here. Outward for both, inward for electron and outward for proton, inward for proton, outward for electron, inward for both. So you have to identify the cases here. So it will be not be same for both. So outward for both and inward for both is a wrong explanation here. And we can see that if I am again going to the diagram here, this is our diagram. So this is our magnetic field. The magnetic field we have is from top to bottom. So forefinger is giving the direction of magnetic field. This is the direction of current. So electrons are moving here. So the direction of the current will be like this. Direction of current will be like this. So I have to orient my fingers in this direction, because if this is the direction of electron, this will be going to be the direction of current, because these both will have a opposite direction. So from orienting the fingers that are mutually perpendicular to each other of your left hand, you can see that the direction of current will be inward for electron and outward for proton. It will be not be same for both, because these are the opposite particles we have. So we can conclude that it will be inward for electron and outward for proton. So which option is correct here? We can see that option number B is correct here. So I hope this question has been clear to you. Now let's move to the next question in this sequence we have. Electric motor is a device which converts. It is a very simple and theoretical question we have, and we have discussed previously in our lecture that motor is a device which is going to convert electrical energy into mechanical energy, because of which most of the electronic devices and electric appliances are working at our home. So it is converting electrical energy into thermal energy. Wrong statement. Electrical energy into mechanical energy. Electric motor is converting electrical energy into mechanical energy. So we do not have to look at the other options, because it is a very simple question that motor is converting electrical into the mechanical one. Now let's move to the next question in this sequence we have. Dynamo works on the principle of. So dynamo is again like a very huge magnet, and it basically works on the same principle on which the magnets are working, and this principle is only electromagnetic induction. So let's check the options here. Electrolysis, wrong statement. Thermal radiation, wrong statement. Electromagnetic induction, same. So because dynamo is having a magnets in it, or we can say that it is a very huge magnet. So its principle will be electromagnetic induction, and it is again a very simple question you have. Now let's move to the next question. The frequency of alternating current supplied in India is. So this is a very simple question. I have told you in India the electricity is supplied only at the frequency of 50 Hz and the potential of 220 volt. So you have to remember this point, that the frequency in India for all the AC circuits or all the supply of the AC current is only 50 Hz. So it is 50 Hz and the voltage or the potential will be 220 volt. Let's see the next question here. This is a numerical type question you have, and for this you have to learn the formulas that are related to your topic transformer that we have discussed in our previous lectures. So, in a transformer, the number of turns in primary and secondary are this. So, firstly, I am writing the given conditions here. What is given here? Number of turns in primary, that will be your NP. NP is 140. Number of turns in secondary. Number of turns in secondary are 280. Current in the primary is 4 ampere. Current in the primary is 4 ampere, then the current in the secondary will be. So, what you have to determine? You have to determine the current in the secondary coil. So, in case of the transformer, we have seen that the ratio of NP upon NS will be equal to IS upon IP. This is the formula for current we have. Now, on substituting these value, NP we have is 140. It is our 280. You have to determine the current in secondary, and the current in primary is 4 here. 0 will be cancelled by 0. 14 1 are 14 and 14 2 are 28, and IS is equal to 4 upon 2, and it came out to be 2 ampere here. So, what will be the correct option here? 4 ampere, 2 ampere, 6 ampere and the 10 ampere. So, we can find out that the current in the secondary coil is 2 ampere here. So, the correct option here will be 2 ampere. So, this is the relation of NP upon NS with IS upon IP in case of the transformer. Similarly, if the question asked in your exam related to voltage, this is the question we have based on current. So, if the question is NP upon NS will be equal to Vp upon Vs. So, this is the relation with voltage. So, what you have to do? You have to just reciprocal these terms. For the current, you have to put secondary condition here, and for the voltage, you have to put the primary condition here. So, these are the formulas you can simply apply for solving such a simple problems. So, just copy this solution from here so we can proceed to our next part. Now, let's move to the next question in this sequence we have. Which of the following can produce a magnetic field? The magnetic field is basically produced by the charges, whether they are in the rest or motion, it doesn't matter. So, check the correct option here. Electric charges at rest, electric charges is motion only by the permanent magnet, electric charges whether in rest or motion. So, they are going to produce the magnetic field whether they are in rest or motion, it doesn't matter. So, we have only D option correct here, both rest or in motion. This is again a very simple and theoretical question we have. Let's move to the next question. And this will be the last question related to your competitive exams we have. A wire is lying horizontally in the north-south direction. So, you can see that the wire is lying in the north-south direction. So, this is our wire. There is a horizontal magnetic field pointing towards the east. So, you can see that this is our magnetic field lines and it is denoted by B, and it is coming from west to east because it is pointing towards east. Some positive charge in the wire move north and equal number of negative charges moving to the south. It means positive charge is going to the north and negative charge is coming to the south. Then you have to identify the direction of the force. I am again repeating the question. This is our current carrying wire, and this current carrying wire is having a magnetic field in this direction. Positive charge is moving upwards, negative charge is moving downwards, and this wire having a magnetic field coming towards east. So, it must be coming from west to east. So you have to find out the direction of the force. So which will be the correct direction here? We have to apply the Fleming's rule for finding the direction of the current. So if magnetic field is in this direction and the charges are moving in this direction, if I orient the fingers of my left hand in such a fashion that middle finger is going to give me the direction of field, this finger is going to give me the direction of current, and this thumb will going to give the direction of the force. As the magnetic field is coming here, you can see that magnetic field is coming here and the negative charges are moving towards, negative charges are moving downwards. So I have to keep my fingers like this. You can see that this is my left hand and I can orient my fingers like this, that magnetic field will be in east direction. This finger moving in downward direction because negative particles are moving here. So you can see that thumb will give you the direction. So thumb is coming outwards. It means out of the wall, out of the page, or we can say that it is in the outward direction. So which option is satisfying here? It will be out of the page. So we can see that up out of the page will be the correct option here. So we have to identify the direction of force in this question. This is our magnetic field lines. This is our direction of, this is wire. And we have seen that an equal amount of positive and negative charge is flowing in this wire. So it will be our positive charge and it will be our negative charge. So if I am going to apply the Fleming's left hand rule here, what I have to do? I have to keep all these fingers in a mutually perpendicular to each other. So thumb will give me the direction of force, forefinger will give me the direction of current, and this finger is giving me the direction of field. So what I am doing here, just visualize yourself that the magnetic field is going towards east and this thumb will give you the direction of the force. So if magnetic field is going like this, we can see that the flow of the current will be just opposite to that of the flow electrons. So the negative charge is here, positive will be here. So the current will be flowing like this. Current will be flowing like this. So it will be the direction of current. So if you have to keep your fingers of the left hand mutually perpendicular to each other, so you can see that if negative charge is moving in the south direction and positive charge is coming in the north direction, so the upward direction will be the direction of current. So it will be like this. It is here and you have to orient your finger in this direction. So if I am doing like this, this is my magnetic field, this is our direction of current and the thumb. So the thumb is pointing inward the wall. It is pointing inwards the walls or into the paper. So what will be the correct option? You can see here. The direction of the force will be into the page, but it will be in little oriented in the downward direction. So we can say that which option is correct here? Option number B is correct here, that is down and into the page. So this is all about your NTSE questions we have discussed today, and you can find here that maximum of the questions can be asked only on the direction of the force or magnetic field here, and you have to remember a simple formula for the transformer for solving simple numerical problems. So these questions are over here. So just see this video lecture very clearly to clear the concept of your NTSE questions here. So this is all about the NTSE questions we have. So thank you so much and have a nice day.